Okay, so this is a bit of a showcase of a collaboration between RISE as an experience center and BP Castrol, one of our partners in our partnership program. So I'm John Summers. A lot of you know me, scientific lead in data centers, and
yeah, I'm Nick Barrett, senior engineer for Castrol.
Great. So what have we been doing in this partnership? So we've got a data center facility up in the north of Sweden, just a few clicks south of the Arctic Circle. Some people have been there, some people have experienced it. It is an OCP experience center. So the idea here is that we've produced a lot of test beds, and we focus on good telemetry, data. Let the data do the talking, okay? So no opinions, it's all about, we're just going to show you some data, we're going to show you the setup, and some data we've got from an immersion system.
And from Castrol, we've developed thermal fluids. So we've put our thermal fluids to test in collaboration with John. And yeah, we continue to support future formulations as well, so continuing research.
So since we're looking at operation, our focus has been on performance. So this is flow rates, temperatures, performance of the IT in the immersion system. So everything you will see is from live IT. It's not the latest generation IT because it's not easy to immerse very expensive systems these days, yeah. As Oriel pointed out about immersing expensive systems, you probably go for TTVs, yeah.
And so from Castrol, our fluids were typically made to always meet the targets that you see on screen, so low viscosity, proven thermal fluids performance, strong electrical characteristics as well, it's really important obviously, but good high fluid stability and not harmful to the environment, so no GWP and no ODP, sorry.
Great. So what we've got is we have a lot of action going on in the facility. So naturally, inside the facility, there are thermal fluctuations. So we've got a little cube here, which becomes a climate chamber. So we can keep the temperature of whatever's in that cube at a stable temperature. So it's connected to our chilled water loop. So we have some air movement. So you can see the two entries for the air, and then we maintain the temperature in there through a control system. But it's directly connected to the chilled water that also goes to 2 production data centers and 2 test data centers as well. And what we've done is on the liquid side, we have a tank here, which allows us to immerse a small amount of IT, and the coolant is circulated out of the tank into a heat exchanger, which is connected to the chilled water loop on the other side. And we have full control over the delta T to the tank, so we can look at the different delta Ts, and obviously we can raise and lower the temperature to see, to focus in on the coolant properties. Okay. So the telemetry side of things is we use open source from beginning to the end. This is a fun slide. So we use Zabbix, which is a very well-established, in fact, it's been around for nearly 20 years, established piece of software which talks multiple protocols. So we can connect it to different devices, whether it's Modbus RTU, Modbus TCP, SNMP. We can talk any REST APIs we can pick up. We can even do calculations on the fly with Zabbix. Really great thing. But when you're collecting a lot of data from different pieces of equipment, the problem is you've got to track what it is you've got. And it's all NTP time stamped, so we use a network time protocol to stamp it, so the log files are all. It goes through what's called NiFi, which is a data provenance tracking system, so this sorts out the keys that we've got. That's another open source software, and the URL for the software is there. Then we have to put it through a streaming meter because we can't store everything in Zabbix, so it's got to end up in a long-term storage database. So we use a streaming platform called Kafka. It's a really great piece of software from Apache, and that allows us to stream the events to the right place. And then, of course, Logstash is another piece of software, open source software, which filters and transforms the data so that we make sure that the keys are correct, and any Zabbix metrics that we haven't picked up that checks that they're there. And then we've got to store it somewhere. So that's where we end up with this Victoria database at the end, with the Victoria metrics database. And then we build our dashboards around that, which talk a very standard piece of software that a lot of people use. Grafana talks to that dashboard talks to that data set so that we can display everything.
So in the setup of the experiment, it's really important that working with John and the team that we created an experiment which is fair, open and fair. So in doing that, we put 4 fluids up for testing. We defined the controls over that, the workloads of the controls, the fluid delta T, the difference between the fluid inlet outlet temperature is controlled, and define the measurement outputs as well. So making sure that we're recording the CPU temperature, pump power, fluid flow rate, IT power consumption as well. And in doing all of this, we've come up with a fair test to make sure that every fluid is tested exactly the same. And I think the next slide goes on to start talking about some results, John.
Some of the results, yeah. So here we have some of the results. So we've got the 4 coolants listed there, and what the top graphs showing you left and right, obviously different delta T's across the I guess it's across the heat exchanger. So a small amount of IT, I can't remember exactly, maybe it was six servers, Dell servers that we put in there. And you can see that there's a difference between the power draw of the IT, both at 6 degrees delta T and 3 degrees delta T. So there's coolant B there drops quite considerably. And that's a result of the current leakages, because the CPU temperature is lower. And why is the CPU temperature lower? I mean, that's something we can talk about a little bit in a minute. But also the pump energy is the third line there showing a decrease. This is all happening at 50 degrees centigrade inlet. So you can see that the temperatures of the CPUs are getting close to their non-ideal case. 80 degrees is quite hot for these. But there's one there that's at 78.
Just to add in, within the fluid matrix, we also tested each of those fluids 3 times. So it's a fair test. The error bars on those results show the minimum maximum deviation between the tests.
Good point, yeah, and they were long-term tests as well, so that we got quite a lot of data.
So very happy with the repeatability of the data.
Yeah. And so there's your winner, if you like, if you wanted to talk about a winner. But we actually did the whole thing. We did it at different temperatures, but we looked at the high and the low end, so the 20 degrees centigrade here, and you can see that you probably can guess what's causing this, why this fluid B is doing so well, this coolant B is doing so well. But again, but one of the things that should point to here is the CPU temperature. The CPU temperature now is down in the 50s, and that's because our inlet temperature is now 20 degrees. And because the inlet temperature is 20 degrees, you can see that the power draw of the IT, there are no fans in it. It's all the microelectronics drawing more power, or less power in this case, is because we're running at a lower temperature. The point I've made a couple of times about current leakages over the course of these 2 days. Probably everybody's fed up with me talking about that.
So yeah, it's nearly a 5% difference between the total power draw between moving from 50 degree inlet temperature to 20 degree inlet temperature. That's significant, 5%.
Yeah, so what you see here is the added, the performance of the IT in terms of the different cases. So this is at 3 degree delta T and at 20 degrees centigrade. So you've got the lowest power draw for the same amount of workload. We're doing the same amount of IT workload. That's the important thing. But then there's another one, which is a best performance system by adding the pump in because we have to pump the coolant into the tank. And so at 6 degrees, when you have a 6 degree delta T, you have a lower pump power. And that adds to the best performance, if you like, on that.
So yeah, overall, the observations from the test that we made is that the thermal resistance, the temperature between the CPU and the coolant set point, lowest thermal resistance was coolant B all the time. The highest thermal resistance was coolant D. And coolant B shows the best performance. So across doesn't matter what temperature you test that, coolant B was always the one that stuck out as being the best performer.
So understanding the application and of course selecting the best coolant is obviously for single phase immersion. I think you need to understand what are the properties of the coolant, and I think there's no doubt in this room that everybody's twigged what's the property that's helping us here. But what we have observed from the data is the reduction in CPU temperature. The lower CPU temperature leads to lower IT power consumption. And of course, the lower pump power consumption. That might be the giveaway, and increasing the cooling flow, of course, with the particular coolant. So in terms of the call to action, I mean, and I'm probably remiss at not joining the immersion cooling group that much, even though Rolf keeps saying, why aren't you there shouting down the line, as I might do. But it's just, there's so many of these calls, you know. But anyway, the call to action here is obviously all of what you've been hearing about the immersion group, the great work they've been doing and the white papers that have been coming out of that and all the thought leadership around that. And of course, as an OCP Experience Center, we wanted to showcase that we're doing a lot of stuff in this space, and that we want to make sure that we are collecting scientifically sound data that we can bring to the community. So, urging you to participate in this immersion group, and of course, you know, obviously, we've put the link there to the Castrol immersion cooling, the coolant properties that they're bringing into the market.
Yeah, so understanding your application, understanding that you've got a choice of fluids to make, but understanding what fluids can bring you in terms of performance benefits is crucial to getting the best out of your systems.
Yeah. So none of this happens without my team, so I have to thank the guys up that have been working on this. They're the guys that get their hands dirty. Håkan Fredriksson and Tina Stark and Adrian Melgren, and thanks to Castrol as well for the support. Thank you very much, everyone. Yeah.
Any questions?
Yeah.
We've got time for questions, Rolf, or? Yeah. Yep, so if there's any questions, happy to take questions. Everybody wants to go home.
Yeah, it's the end of the day.
No.
Go on, Andy. Yeah.
Dare I say, without wanting to be pedantic? No. No. I know, I can't think of one. So, actually, Pete and I were just sort of whispering to each other while you were talking, and we were wondering if you monitored the frequency of the processors alongside the power during your testing.
Good question, yeah. I mean, no. You know the answer is going to be no. I mean, it's not easy to do. You mean the actual whether they were throttling or their frequency of yeah.
Yeah, you can infer it in some ways from the power, but the power is affected by a number.
So we're running turbostat, and we're tracking. We run a fictitious workload, but it was running at 100%. And turbostat tells you what the...
It's also, then, what you saw there was a snippet of the data from the overall project. It was much bigger than what we've shown today.
So if we were to see the frequency, you basically see that it was consistently good across all the testing, I'd imagine.
Yeah, so you're asking the question, let's get this right, because you were talking about a different thing about frequency, or signal integrity. This is actually the frequency
of the clock frequency.
Yeah, the clock frequency, yeah. No, they weren't throttling at all.
Yeah,
no,
okay.
Absolutely not. Because if they were, we would be, the data would be misaligned. Yeah.
Thank you.
Trust me, I'm a scientist.
I trust you, John.
Thanks a lot, yeah.
Thank you for having us. Thank you.